All right, so good morning, everyone, and welcome to another lecture for the 124103 Biophysical Principles. This is the second week of the semester, and I hope your first semester has gone well and you're ready for another round of lessons this week. So let me share my screen so we can start looking at, make sure I look for the chat and the participants' screens. So just bear with me for a second there. I'm just trying to set up so I can see the chat box in case there are questions. All right. Okay, so I hope you can see the screen that I'm sharing. It's the PowerPoint slide for today. So some thumbs up, some confirmation would be good to make sure before I begin, you can see what I'm, okay, good. You can see some thumbs up there. Great, thank you. All right, so last week we started our lesson by talking about a moving object, and we learned how to describe the motion of that object in terms of its distance and displacement, speed and velocity, and also acceleration. And then we also started learning how to interpret the motion of an object that's represented using graphs. So in this lesson, we will continue from where we left off. We will still look at the motion graph of an object, and from that graph, what kind of information we can get regarding the motion of an object. All right, so hopefully at the end of the lecture, you will be able to determine the velocity and displacement of an object using its motion graph. Okay, so a little bit of revision from last week's lesson. So this is the motion graph of an object showing the position x, okay, versus time. So again, when we say position versus time, it's the y-axis will contain the position and the x-axis will contain the time. So if you look at this graph here, the y-axis is the position x measured in meters, and the x-axis is the time measured in seconds. The graph here is this straight line that shows us how the position of the object changes as time goes on. And we learned last week that if we have such a position versus time graph, we can take 2 points along that graph. So say this point here, which gives us the final time. And this point corresponds to the final position xf at that time tf. And we can take another point along that line, say, for example, this point here at an earlier time, and we designate that as the initial time ti. At that initial time ti, the object is at this initial position xi. And if we have these 2 points along this line here, we are able to calculate the slope of this line. The slope is defined as the change in the value in the y-axis divided by the change in the value in the x-axis. Okay, the y-axis is position, therefore change, you have final minus initial. And so you have the final position minus the initial position, okay, and divide that by the change in the x-axis. Your x-axis is given as time. So the change in time will be the final time minus the initial time. TF minus TI. Looking at the units for this, the unit for the position is meters, and the unit for the time is seconds. Therefore, the unit for the slope will be meters per second. And we've learned that velocity has the unit of meters per second. Therefore, the slope of this position versus time graph will give us the velocity of the object. between this time interval, Ti and Tf, right? And similarly, if you're given a velocity versus time graph, so that means velocity will be in the y-axis, velocity, and then time will be on the x-axis, measured in seconds. And this graph represents our velocity versus time graph. The graph is a straight line that's going downwards. In a similar manner, we can take 2 points along this line. Okay, so this point here with a final time TF corresponding to a final velocity VF. This point here giving us the initial time TI corresponding to the initial velocity VI. And in a similar manner as the position time graph, we can get the slope of this line as the change in the y-axis, which is change in velocity VF minus VI, divided by the change in the x-axis, which is the change in the time TF minus TI, giving us, in terms of units, meters per second for the change in velocity and seconds for the time. And therefore, the slope is equal to acceleration. Okay. So you have to be aware, look at what the y-axis is giving you. If the y-axis is velocity, then the slope will be acceleration. If the y-axis is position, then the slope will be velocity. All right. And in the workshop, so I just want to point something out in the workshop, in the second workshop, where you explored the acceleration of the moving man in the PhET simulation. Hopefully, one of the questions in the workshop was like, put a positive acceleration for the moving man and observe what's the shape of the position time graph. So say if you have this moving man PhET simulation, this PhET simulation here, and if you put, say, a positive acceleration there, and you, let me just think my moving man. So say you put a positive acceleration, initial positive acceleration for you moving man, and try to investigate how his position and velocity and acceleration time graphs look like. Okay, hopefully you're able to see something like this. So you see here the acceleration is positive. So put here, so for example, positive 2 meters per second squared. You have a constant positive acceleration. And just moving backwards, so that corresponds to a velocity that's a straight line that's going upwards. So in other words, if you get the slope of this velocity time graph that is a straight line that's going upwards, the slope of that will give you a constant positive acceleration. So that's just a straight line with a positive value for the acceleration. Now the question is, what shape of position time graph will give you a velocity that is a straight line that's going upwards? Because we have already learned that if you have a position time graph and get the slope of that position time graph, you should get the velocity. So if the velocity is a straight line that's going upwards, what's the shape of that position time graph whose slope will give you this straight velocity time graph? And hopefully you've seen in the PhET simulation that, okay, that if the position time graph is a curve that curves upwards, the slope of that will give you a straight line graph that's pointing upwards. So one way to remember this is a positive acceleration gives you sort of a smiley face. Right? Okay, so being positive, you're smiley. So a positive acceleration corresponds to a position time graph that's sort of smiling, curved upwards. Right? And if you have a negative acceleration, okay? If you have a negative acceleration, what would be the shape of the position time graph that will give you a negative acceleration? And hopefully by doing the PhET simulation, you were able to see a graph for the position time graph that looks like this. It's a curved line that's going downwards. So if we retrace our steps backwards again, if you have this acceleration that's constant and negative, okay, the velocity time graph of this will be a straight line that's pointing downwards. In other words, if you have a velocity time graph that's straight or linear and it's pointing downwards, if you get the slope of this velocity time graph, that will give you a negative value that's constant, meaning the acceleration will be constant and negative. And this velocity time graph that's straight and pointing downwards will have a position time graph that's curved downwards. So if you get the slope of this position time graph that's curved downwards, you should get this velocity time graph that's straight and pointing downwards. So in other words, the reverse of the smiley face is a frowny face. Okay, a frowny face sort of gives you a negative acceleration. So a negative acceleration corresponds to a frowny face position time graph, a curve that's curved downwards. Right? Okay. Okay, so there's scrunchy noises. Sorry about that. So let me just fix that for a moment. Okay, yeah, hopefully that's better. If the scrunchy noise is there, just please let me know. Right. So okay, so if we then have, so to summarize our motion graphs, if you have a motion graph that's position versus time or displacement versus time graph, the slope of that will give you the velocity. So here you have in this graph here, position x position on the y-axis and time on the x-axis. See, if you have a position time graph that's going upwards, the slope of that will give you the velocity, and an upwards straight line position time graph will give you a constant positive velocity. And if your position time graph is straight line and pointing downwards, the slope of that will give you a constant negative velocity. Okay. So position time graph, the slope of that will give you a velocity. And if you have a velocity time graph, so this graph on the right here, the y-axis is velocity and the x-axis is time. So in that case, the slope of the velocity versus time graph will give you acceleration. And if your velocity time graph is a straight line that's pointing upwards, then the slope of that will be a constant positive number value, which will give you a constant positive acceleration. Right? Okay, does that sound okay so far? It's just revising or reviewing what we learned last week about motion graphs. All right, good. Okay, so if that's okay, now the question is it possible to go backwards? Meaning, is it possible to use the acceleration time graph and obtain the velocity? And is it also possible to use the velocity time graph and obtain the displacement? And that would actually be our lesson for today. Okay, in fact, of course, the answer is yes, because otherwise we won't be learning that today. So if you have the acceleration versus time graph, if you get the area under that position, under that acceleration versus time graph, then you would be able to get the velocity. Okay. And if you have a velocity versus time graph and you get the area under that velocity versus time graph, then you would be able to get the displacement of the object. So yes, the answer is it is possible to go the other way. So that if you have an acceleration versus time graph, you will be able to get the velocity. And if you have a velocity versus time graph, you will be able to get the displacement. But instead of finding the slope, you need to find the area under the graph in order to find these quantities, velocity and displacement. Okay, and so now we will learn what this area under the graph means and how do we actually get this area under the graph. So it's very common if you read the textbooks or search Google, read the internet, it's very common to call this as the area under the graph. Okay? But I would actually like to put quotation marks between this area under the graph, because sometimes it's misleading. It's not actually always the area, it's not always under the graph, sometimes it's over the graph, and we'll see that here. So for example, you have a velocity versus time graph. So a velocity versus time graph again means that the y-axis plots the velocity and the x-axis plots the time. Okay, so the graph, the actual graph is this blue line here. Okay. So when we say area under the graph, we are actually determining the area between the graph and the horizontal axis. So we want to find the area between the graph and the horizontal axis. So for example, here in this graph, the area that you want is between the graph and the horizontal axis. So for this portion of the graph that I've shaded in yellow, that's the area that you want to calculate. It's that space between the graph. This is the graph here, the line, the blue line, and the horizontal axis. Okay. And if the area is below the horizontal axis, that means that the displacement is negative. Okay. So this area here I've shaded with yellow, it's below the horizontal axis. So that means if you get the area of this shaded part here, that will give you a negative value, and that means that the displacement is negative. If you look at the values for the velocity values are also negative, and we learned last time that negative velocities mean that the object is moving to the left or moving downward, and that gives you negative displacement, right? Okay, so negative displacements mean that the area you're calculating is below the horizontal axis. Okay, and then the opposite of that, if the area you're calculating is above the horizontal axis, like this blue shaded area here, then that means that the displacement that you're calculating will be positive. And again, if you look at the values of the velocities above the horizontal axis, you have positive velocities. And positive velocities mean that the object is moving to the right. Okay? And therefore, your displacement will be positive, okay, moving to the right. Does that sound okay? Does that make sense? Good. All right. So the key takeaway message in this slide is if you have a velocity versus time graph and you wanted to find the displacement of the object, then you need to calculate the area between the graph and the horizontal axis. And if that area that you're calculating is below the horizontal axis, that will give you negative displacements. And if the area you're calculating is above the horizontal axis, that will give you positive displacements. All right, cool. All right, and if you have an acceleration versus time graph, okay, so the y-axis is acceleration, units is meter per second squared, and the x-axis is time, the unit is seconds. Then if you wanted to find the velocity, the change in velocity, then you have to calculate the area under the graph, and under the graph again means that you're calculating the area between the graph and the horizontal axis. Right, and in a similar manner, so this is the graph. The graph is this straight black line. It tells you the value of the acceleration at different times. And if you wanted to find the velocity between this time interval, the change in velocity between this time interval, TF and TI, then you need to find the area between the graph and the x-axis, so that's this blue shaded line here. And if that area is above the horizontal axis, then that also means that the change in velocity is positive, right? Which could mean that you are speeding up or that you're moving in towards the right or upwards. Okay. And if your acceleration is negative, so in the graph here on the right, the acceleration graph again is this straight black line here, giving you a negative value for your acceleration. So the acceleration is negative and it's constant. It's the same at any time. If you wanted to find the velocity of this motion between the time intervals Ti and Tf, then you need to figure out the area between the graph, the acceleration graph, and the horizontal axis. And that's this pink shaded area here. And this pink shaded area is below the horizontal axis. So that means that the change in velocity will be negative. Okay, and a negative change in velocity means that either your object is slowing down so that its final speed is smaller than the initial speed, or that your object is moving to the left, to the negative direction. All right. Okay, so does that make sense? Okay. If you have a velocity versus time graph, the area will give you the displacement. If you have an acceleration versus time graph, the area will give you the change in velocity. Right. Okay, so that's the key idea behind how you can use the motion graph to find the velocity or the displacement. Now, the next question is, how do we solve the area? Right, we know that we need to figure out what the area is, but how do we actually solve for the area? So you can see here for the acceleration time graph that the area actually traces a geometrical shape. So the area here looks like a rectangle. And so to figure out this area, we need to know how to solve the area of a rectangle. Okay, so the area of the rectangle requires you to multiply the length, the longer side of the rectangle, with the width or the shorter side of the rectangle. So if the shaded area between your graph and the horizontal axis looks like a rectangle, then you can solve that area by multiplying the length of the rectangle with the width, multiply the length with the width of the rectangle. If the shaded area looks like a triangle, then you can figure out, you can calculate the area by using this equation for the area of a triangle, which is 1/2 multiplied with the base multiplied with the height of the triangle. So the base there is this horizontal, the shorter side, and the height of the triangle. Okay. Any other geometrical shapes can be broken down as a combination of a rectangle and a triangle. So even if your shaded area is an irregular polygon, okay, an irregular geometrical shape, you can always break that down into rectangles and triangles and solve the areas of these triangles and rectangles. But there's also another common geometrical shape that we often see, and so it may be useful to find to know what the equation of the area of this geometrical shape. It sometimes makes life easier, and that's a trapezoid. A trapezoid is a geometrical shape that has two sides that are parallel. So two parallel sides, and these two parallel sides are called the bases. So you have here base 1 and base 2, and two non-parallel sides. And these two non-parallel sides are called the legs. So this is an example of a trapezoid, the figure on top. This figure below is also an example of a trapezoid. You have two parallel sides called the bases and two sides that are non-parallel. And the area of a trapezoid can be calculated using this equation, 1/2 multiplied with the height of the trapezoid. So the height is the distance between the two parallel sides, okay? The distance between the two bases of the trapezoid, that's the height. Okay? Multiply that with the sum of the two bases. So base 1, the length of this side, base 1, plus the length of this other side, base 2. The sum of the two parallel sides. Yeah. So if you're using a calculator, sometimes be aware of the bracketing. If you enter this in the calculator, make sure that you put brackets to enclose your base 1 plus base 2. Otherwise, your calculator might just multiply height with base 1. Or a simpler way would be to add the two bases first and then multiply that with the height and 1/2. Okay. Yeah. So again, the tests and the exams are open book, so you don't have to memorize these equations. But I would do suggest that as we go along, you probably make a formula sheet that you can easily refer to whenever you need to look at formulas to answer questions. All right, so these are probably the most common geometrical shapes that we'll encounter. So for example, for this acceleration versus time graph, as we can see here, the shaded area between the graph and the horizontal axis is rectangular. So you can just use the area of a rectangle. Let me change my pen. Okay, so you can just use the area of a rectangle, the equation for, just rub that off. The equation for the area of a rectangle will be equal to length times the width. Okay. So that will be this area here. The length will be TF minus TI. That's the length. And multiply that with the width, which will be the value of your acceleration. Okay. Right. So if it's a simple geometrical shape like a rectangle, you can easily calculate the area of that using one of the formulas that we've seen. And now, what if your motion graph is a bit complex? So say, for example, this velocity versus time graph here. The graph again is this line, the black line here, and you want to figure out the displacement, the total or net displacement of the motion. So you know that you have to calculate the area between the graph and the horizontal axis, but the graph is irregular. Okay, so you can always divide an irregular shape, as I've mentioned earlier, into triangles and rectangles, and then add up all those individual areas, accounting for signs, meaning if your area is above the horizontal, that's a positive displacement. Areas below the horizontal will give you negative displacements. And then after adding up all those areas, that will give you the total or net displacement. And remember that you want to find the area, meaning of the space between the graph and the horizontal axis, right? So for example, in this graph here, we can divide this area. So you can have this as your first area. Okay, you can figure out what the area of this triangle is. 1/2 multiplied with the base multiplied with the height. So you can say, yeah, so this is the first area that I have to figure out. And then with this portion here, it's an irregularly shaped thing. So you can divide that, for example, into a series of, so that's a triangle, and you can divide this like that, so that you have a triangle here, a triangle there, and you can even further divide this. Okay. So you have here a triangle, and you can say this will be the second area that I have to figure out. And you have here another triangle. And you can say that's the third area that you need to figure out. And you have here a rectangle. And you have to figure out the area of this rectangle. And then finally, you have this tiny bit of a triangle here. And you also have to figure out, let's say that's area 5 that you have to figure out. So this irregularly shaped space between the graph and the horizontal axis can be broken down into a series of triangles and rectangles whose areas you can easily calculate from the equation. And then you still have this portion of the graph that you have to figure out. And if that's the final time there, your motion stops at this point. So that traces out a triangle. So that will be, what color, right? So this will be the final area that you have to figure out. Okay. So that's area 6. Okay. So yeah, you have to then calculate the areas of each of these geometrical shapes. So then the total displacement of your object will then be equal to the area of the first shaded portion plus the area of the second shaded portion plus area 3 plus area 4 plus area 5 plus area 6. So you need to add up all the areas. But next, don't forget to account for the signs. Okay, account for the signs. So looking at these areas here, which areas are actually negative? So some areas here are positive, some areas are negative. So which areas are actually negative in this graph here? Yep, very good. Good. I can see correct answers in the chat box. So we said that any space below the horizontal axis will give us negative areas. So this area 2, 3, 4, 5, they are below the negative axis. So actually area 2, I think I erased too much. Yeah, I just wanted to erase the signs. Okay, so area 1. So actually area 2 should be negative. So you should be subtracting that. So A1 minus A2. Area 3 should also be negative, and so is area 4 and area 5. Right? Okay, good. So yeah, you have to be careful with the signs when you're adding up different areas. If your area is below the horizontal axis, you should be subtracting that area because that area is negative. Right. Cool. All right, is that all right? Any question about that, or are we happy with that? Good. All right. So silence means probably it's okay. Yeah, so here we've divided this into triangles and rectangles. And you will see here that maybe, and so we have 6 areas that we can add, and this is totally legit. This is the simplest way you can do it. But again, that's why I discuss about the trapezoid, because if we know the area of a trapezoid, then we can actually simplify this. Instead of adding up 6 areas, we can actually divide this irregularly shaped area into 2 portions, and we can see that this is a triangle here. Okay. And the area above is actually a trapezoid, right? Right? So you actually have these 2 bases that are parallel and these 2 legs that are not parallel. So yeah, it's totally up to you. If you can easily visualize that there's a trapezoid in this irregularly shaped area here, then you can just divide it into a trapezoid and a rectangle. Sorry, a trapezoid and a triangle, and you should still get the same value for the displacement as if you've divided this area into rectangles and triangles. Okay. We'll look at a numerical example of that later on, but yeah, but essentially you can divide this irregularly shaped part into a trapezoid and a triangle, or triangles and rectangles. It's totally up to you. Okay, does that sound okay? All good? Or are there any questions so far? All right, then let's move on and look at this example, and now with numbers, and see how we actually find the displacement of the object. So determine the displacement between 0 and 5 seconds. So the first thing, whenever you're given this kind of question or problem, is to check what is the y-axis in your graph. So your y-axis is velocity. Okay, your x-axis is almost always going to be time in motion graphs. Okay, so your y-axis is velocity. So if you wanted to find the displacement, are you going to use the slope? Are you going to solve for the slope of the graph or the area between the graph and the horizontal axis? Yeah, good. All right. So if you have a velocity versus time graph, the area will give you the displacement. So say that's 5 seconds. So for example, that's where 5 seconds is. We want to find the displacement in the first 5 seconds of the trip. We have to figure out, as you've said, we have to figure out the area between the graph, this straight line, and the horizontal axis. So we have to figure out what's this area here. Right. The shaded area is a rectangle, so it's relatively a simple geometrical shape. The area of a rectangle is equal to the length times the width of the rectangle. Okay. Right. Length is how long that side is. It's 5 seconds times the width, how long that is. Yeah, -5. So it's up to you. You can either use the -5 there, or you can use 5, and then you know that it's so that's -25 meters for the displacement. So the area of the rectangle is -25 meters. Therefore, the displacement will be equal to -25 meters, or 25 meters to the left. Negative sign means the direction is the left. Right. So in getting the area, it's totally up to you whether you put the negative sign in the width. So here in my calculation, I've included the negative sign there, and that automatically gives you a negative number for your area. Or you can just use the actual width, which is 5 meters per second. And then in your final answer, just check whether the area is below the horizontal axis or above the horizontal axis. If it's below the horizontal axis, then you know that your area will be negative, your displacement will be negative. Right, there's a good question in the chat box. So the unit, will the unit be meters squared or just meters? Right, so we're getting the displacement. That's the area under area of this portion here. And the unit for displacement is meters, because it's your final position relative to your initial position. So the unit for displacement is meters. So that should be in meters. If we figure out the unit from our equation, so the area of a rectangle is equal to length times width. Okay, the unit for the length is this 5 seconds. So the unit for the length is seconds. Okay, multiply that with the unit for the width, which is the velocity, meters per second squared, meters per second rather. Yeah, meters per second. Yeah. So you're essentially multiplying the unit seconds with the unit meters per second. There's a mathematical rule that if you're multiplying two things that are at the opposite side of the division bar, those two things, any number, those two things will be equal to 1. The mathematical rule is this: any number divided by itself is equal to 1, which means 2 divided by 2 is equal to 1. That also holds if you use units or symbols. So for example, seconds divided by seconds, you're dividing seconds by itself, that will give you 1. Or meter divided by meter, meter divided by meter, that will also give you 1. So any number or anything divided by itself is equal to 1. And in this working out here, seconds times meter divided by seconds, you're essentially, you can write this down as seconds times meters divided by seconds. So you're essentially dividing seconds by itself, and that will give you 1. So that's 1 times meter. Anything multiplied with 1 is the same thing. So that will be meters. So this is the mathematical working of why the unit for the area of a velocity time graph is meters. Okay. But you can also think about it in the sense that you are finding the displacement, and the unit for displacement is meters. Right. Does that make sense? Yeah. Cool. Right. Meters per meters per second squared will be the acceleration. That's when you get the slope. Displacement, the unit is meters. Good. All right. Cool. Right. So relatively simple geometrical shape, a rectangle. Right. So now what if we wanted to determine the displacement between 11 and 14 seconds? Okay. So say 11 seconds is, say, for example, this point here. And you can read off the graph what's the value of your velocity at 11 seconds, and 14 seconds is this point here. Right? So this is the later time t, that's your earlier time ti. So between these 2 points, you can sort of read off, this is your final velocity, and that's your initial velocity. All right, so you want to figure out the displacement between 11 and 14 seconds. All right. So how do you figure this out? So I'll give you a few minutes to try and figure this out. Maybe think about the problem or start working towards the solution, and then we'll look at how we solve and answer this question. Cool. Right, so I can see some correct answer on the chat box. So let's look at how we solve this question here. So we're wanting to find the displacement between 11 and 14 seconds. First thing we need to check what's on the y-axis. So your y-axis is velocity. It's a velocity versus time graph. If you want to find the displacement from a velocity time graph, you have to calculate the area between the graph and the horizontal axis. That means you need to figure out what's the area of this shaded portion here. Right? Okay, if you're looking at this shaded portion, you can see that two sides are parallel. Right? So you actually have two parallel sides. Okay, base 1 and base 2, those are the two parallel sides. So it's actually a trapezoid because you have two sides that are parallel and there are two sides that are not parallel. Okay, so the two sides, those are the bases, base 1 and base 2. Okay, and then the area of a trapezoid, is 1/2 times the height of the trapezoid times the sum of the bases, base 1 plus base 2. Right, the height is the distance between the two bases. So this is the height. Oh, yeah, I hope that's still, yeah, you can still read it. So the height, it's the distance between the two bases. So we can sort of figure out now the values to substitute in this equation. So 1/2 times the height. The height is this length here, 14 minus 11, which is 3, times the sum of the bases. So base 1 will be this 1, 5. The length of this side, which is 5, plus the length of the other parallel side, which is 10. Right. Okay, cool. You can plug that into your calculator. Yeah, the answer is 22.5 meters. That's correct. If you're not getting 22.5 meters, if you're plugging these numbers in the calculator, make sure you put a bracket to enclose 5 plus 10. Okay, or you can also just add 5 plus 10 first. That will be 15. Multiply that with 3. Multiply that with 1/2 or 0.5. You should get 22.5 for the area of the trapezoid. Okay, and the area will give you the displacement. Therefore, the displacement will be 22.5. The unit is meters. And finally, as a final check whether you should have a negative or positive displacement, right? The area is above the horizontal axis. Your velocities are also positive. That means that your displacement should be positive. So that's positive 22.5 meters. All right. Good. Does that make sense? Right. Of course, if you divided this area into a rectangle and a triangle, and you and you solve the area of this triangle and added that to the area of this rectangle, then you should also get 22.5 meters. You should still get the same answer, except that you'll be calculating two areas, adding them up, instead of, if you use the trapezoid, then you're just calculating one area. All right. Right. Any question about that, or some thumbs up if you're happy with the solution and it makes sense? Good. Right. Happy. All right. Okay, very good. So that's how we solve for the areas. Now let's look at this exercise, which will sort of tie up what we've tied together, what we've learned so far about motion graphs, the slope and the area. We are given here the velocity versus time graph of a bee's flight. So it shows us the motion of a bee as it flies about. Okay, so the graph there is this blue line here. X-axis is time in seconds, y-axis is velocity in meters per second. So try and answer the questions here. First one is determining the average acceleration in the first 10 seconds. Second one is the instantaneous acceleration at these two specific times. Third question is determining the displacement between this time interval. And the last question is determining the net displacement. So I'll give you a few minutes to look at the problem, maybe think about it, think about whether you should get the slope or the area to solve for the acceleration or displacement. Maybe you can start solving the problem, and then we'll look at the solutions after a few minutes. Okay, maybe we can look at the first question. We want to find the average acceleration of the bee in the first 10 seconds. So that will be this portion of the graph here. Yeah. In the first 10 seconds, from 0 to 10 seconds. Okay, so if you wanted to find the acceleration given the velocity versus time graph, are you going to solve the slope or the area? Yeah, very good. Yeah, so I can see correct answers in the chat box there, right? Velocity versus time graph, the slope of that will give you the acceleration. So acceleration is the change in velocity over change in time. So you can take 2 points along. So it's a straight line graph. So you can take 2 points along your straight line. Again, it can be any 2 points. As long as it's along that straight line, it should give you the same value for the slope. I'll take the 2 endpoints because you can easily read off the graph the values of the final and initial velocities and times, right? So taking these 2 points here, 2 endpoints, you have here your final time, okay, corresponding to that point there. This is your initial time, that's 0. The origin, the beginning is 0. Okay. And then the velocity corresponding to the final time, this will be 60 meters per second. That's your final velocity. And your initial velocity is the velocity corresponding to your initial time. And it's at the origin, so that's 0. Okay. Right, so you now have your final and initial velocities and time, so you can calculate the slope, which is also the change in velocity divided by the change in time. Right, so the final velocity is 60 minus the initial velocity divided by the final time is 10 minus the initial time, 0. That will give you a slope of 6 meters per second squared. You get a positive number. So as a final check, look at your graph. Your graph is going upwards, a straight line that's going upwards. So that should tell you that you should have a positive slope. Your acceleration should be positive, and it's a constant number. So a positive acceleration means that your speed is increasing and you're moving to the right. Positive acceleration means your B is moving faster as time goes on and it's moving to the right. Good. All right. Cool. Second question, we want to find the instantaneous acceleration at 30 seconds. So again, instantaneous, it's the acceleration at a specific time, a single time, and that's why it says 30 seconds. Okay, so that's the acceleration at this point. What's the acceleration of the B at that point? So again, look at the graph. It's a velocity versus time graph, and you're wanting to find acceleration. That tells you need to find the slope of the graph at this point. Instantaneous acceleration means you have to draw a line that's tangent to this point that you're wanting to find. But your graph is a straight line graph, so essentially the tangent to that point at 30 seconds is the actual graph itself. Okay. Yep, so the velocity time graph is a straight line. The slope gives you the acceleration, but if it's a straight line graph, the tangent will be the graph itself. So find the slope of that at 30 seconds. You can again take any 2 points along that line. It should give you the same slope. I will again consider the two endpoints just because it's easier to read the values of the velocities and times at those two endpoints, right? So this will be corresponding to your final time for this endpoint there. And you can read off the final velocity corresponding to that final time. Okay, the earlier time from this endpoint is here, which is, so each grid is 5 seconds. So your initial time will be 15 seconds and your initial velocity will be 60 meters per second, right? Okay, so you have there your change in velocity, final velocity minus initial velocity, and you have here the run, the change in time. So we find the slope, or we find the change in velocity divided by the change in time. Okay, be careful here now. So your final time is this point here at a later time. The velocity at a later time is negative 40 meters per second. So that's your final velocity. Make sure you include the negative sign in your calculation. So you have negative 40 for your final velocity. Okay. Your initial velocity is the velocity at the earlier time, and that is 60 meters per second. So change in velocity is final minus the initial. That's why you have this negative sign here. This is the minus sign. Final velocity, that's the final velocity minus the initial velocity. Your initial velocity is positive 60 meters per second. Divide that by the final time, which is 40, minus the initial time, 15. Right, negative 40 minus 60 is negative 100 divided by 25, which is 40 minus 15. You should get negative 4 meters per second squared for your acceleration. Right, final check. Your acceleration is negative. Check that against the graph. Your graph is a straight line that's pointing downwards. A downwards straight line graph means the slope is negative. And so, yeah, that's correct. Your acceleration should be negative, and it's a straight line graph, so it should be a constant acceleration. Right? If you don't get negative 4 when you're using your calculator, maybe try putting brackets before dividing, okay? So that, yeah, it's just that some calculators don't automatically apply the mathematical rules. So that could be the problem if you're not getting -4 as the numerical answer. Right, so what does this negative 4 meters per second squared acceleration mean? A negative acceleration means that either the object is moving slower, so that its final speed is smaller than its initial speed, giving you a negative change in speed, or the object is maybe speeding up, but it's moving to the left. Okay, so if we look at this graph here, the portion of the graph above the horizontal axis, you have positive velocities, but then your velocities are decreasing. So this is the point where the B is slowing down, because the, you can see the speed is decreasing as time goes by. And then if you look at this portion of the graph here, notice how you have, speed. Speed is just the positive values for velocities, disregarding the negative signs. So if you look at this portion of the graph below the horizontal axis, the speed is actually increasing. So the B could be speeding up, but because it's negative, that could mean that the B is moving to the left, right? So this portion of the graph here is the point when the B is moving to the left. Change direction and move to the left. Right. Cool. Right. Any question about this solution? Or are we happy? So right. Okay, so maybe it's okay. I don't see any questions in the chat box. Right. So for the 12 seconds, right, 12 seconds, it's instantaneous acceleration. It's at a specific time, which is here. This is about 12 seconds. Okay, you have to figure out again the slope. If you're given velocity time graph, the acceleration is the slope. But here you have a straight graph, meaning it's a horizontal graph, which means that your velocity is the same all throughout between 10 to 15 seconds. So here you have a constant velocity. That means your acceleration is 0. Acceleration is the change in velocity divided by the change in time. So yeah, Keelan, you're correct. The acceleration should be 0. Right? No need to calculate anything there. So the next question, the displacement of the B between 40 seconds and 55 seconds. So it's this portion of the graph here. Yeah, between 55, sorry, it should just be, yeah, that portion of the graph there. Yeah, this is about, yeah, that's right. Sorry, that's 55. So it's the whole graph all the way to the end point there. Right. And since acceleration is from the slope, displacement will therefore be from the area. So it's the area between the graph and the horizontal axis. So it should be this area here. Yeah. The area between the horizontal and the graph, velocity versus time graph, will give you the displacement. Yeah, that area there. And it's a triangle. Yay, so it's a triangle. We know the area of a triangle is 1/2 base times the height. Right? 1/2. The base is, this is multiples of 5. So 5, 10, 15 times the height is 40. Good. Right, that should give you, oh, sorry, I didn't know. So let me just erase this whole thing. Yeah. I didn't know I had animation there. Yep, area of a triangle. So the base is 15 and the height is 40, or you can also now include the negative. That would give you a negative 300 meters. As a final check whether your area is below the horizontal axis or above the horizontal axis. Okay, so be careful now with the sign. Because you're talking about displacement, you need to have this direction, this sense of direction. And that would be a negative displacement because the area you're calculating is below the horizontal axis. Okay. Yeah. If you've included the negative sign in calculating the heights, in calculating the area, because the height, essentially this is the height, you're measuring that side here, and that's a negative 40. If you've included the negative in your calculation, that should automatically give you a negative 300 meters. But yeah, just as a final check whether your area is below the horizontal axis, in which case you should have a negative displacement. Right? So moving to the left, negative displacement means moving to the left. And finally, the net or total displacement of the B. That means you need to find the total area between your graph and the horizontal axis. So all of these areas here. Right. So area between the whole graph and the horizontal axis. Looking at the graphic, I can divide this into two geometrical figures. You have a trapezoid. Okay, because you have these two sides that are parallel. You have the basis and you have the height. And I can also have this triangle here. So essentially you have base 1, base 2, and the height of your trapezoid. Okay. And you have here your triangle. This is the height of your triangle, and this is the base. All right. Okay, so we know that for a triangle, the area is 1/2 times base times height. For a trapezoid, 1/2 times height times base 1 plus base 2, right? So that for the trapezoid, 1/2 times the height is 60, right? Times base 1 is 5, because one grid is 5 seconds, plus you have 5, 10, 15, 20, 25, 30 for the base 2. And then for the triangle, 1/2 base is 25, 5, 10, 15, 20, 25, times the height 40. Or here you can also again now include the negative sign in your 40. And that should take care of subtracting the area of the triangle from the area of the trapezoid. And that should give you 1,000 meters. All right. Cool. 550. So I'm not quite sure how 550 came about. Oh, miscalculation. Okay, good. All right. So 1,000 meters should be, yeah. Be careful with the brackets. If you have the same equation as me and your numbers are exactly as I have them on the screen here, but you're not getting 1,000 meters, try putting brackets, especially bracketing these two. I find that all calculators are different, so. So if the displacement, if the displacement of the half of the green triangle is negative 300, oh, that's from here. Yeah. So this is, okay, I think, yeah, that's a very good, that's a very good, yeah, that's a very good point, actually. And then I think we should check, so this is 5, 10, 15, 20, 25. So that's 25. That's right. I probably need to check here. So your base, 5, 10, 5, 10, 15. 1/2. That's a very good point, actually. So base times height. Oh yeah. Okay. No, that's a very good question. So notice for this portion of the graph here, the B started to maybe change direction here because now it's going upwards, right? So in this second part of from 40 to 55 seconds, the B actually changed directions, right? So the velocity time graph is now going upwards in a straight line that's going upwards. So that means the B changed its direction. It's now moving to the right instead of moving to the left. Okay, and so the total displacement of this whole, so here B is moving to the left for this portion here. And this portion here, the B is moving to the right. Did I do a, so that will be 25 times 40. Oh yeah, yeah. Yeah, you're actually right. Because then that doesn't make sense. Yeah. Thanks for the correction there. It's actually minus 500. So that will actually give us 550. Yeah. Yeah, good. All right. Yeah, good. All right. Sorry about that. Yeah, I was missing a 0 there. So the net displacement is 550 negative. All right. So okay, that's, we're happy with that. Yeah. Good. So thanks for the correction there. Negative 500. So the net displacement is 550. Okay. Good. This is still the same problem. It's just that you can divide this into triangles and rectangles, but it should still give you the same answer of 550. But we don't have to go through this because just doing the trapezoid thing is actually simpler, and it will give you the same answer anyway, but you're just calculating two areas there. So essentially that that answers all the questions in the exercise. And so this table here is probably quite useful to refer to when you're looking at problems with motion graphs and you're being asked to find the displacement, acceleration, velocity, and acceleration. Okay, displacement versus time graph gives you a velocity if you get the slope. Velocity time graphs gives you acceleration if you get the slope. Acceleration versus time graph gives you velocity if you get the area, and velocity time graph gives you displacement if you get the area. All right, cool. All right, that's good then. Any questions about the lecture? Okay. Then, yeah, if there are no questions, then we can jump into the workshop. Let me just stop the recordings.